Example number 4, time-dependent heat equation, parabolic partial differential equations. So we have the problem here, the partial of u with respect to time, t, equal to the alpha times the second partial of u with respect to x. So we have the domain of x from 0 to 1 here. So with u, if x equal to 0 here, so u equal to 0. If x is equal to 1, u is also equal to 0. And initial condition here at that time equal to 0 here. So u as a function of x only is equal to x times 1 minus x. So this is the initial conditions. So Galerkin in the space finite plus finite difference in time. So choose a single trial functions. Choose u as a function of x and time, approximately equal to c of t time sine pi x. So c here is a function of time, which satisfies the boundary condition at all times. So we have the residual here. It's the given partial differential equations. So we substitute here the uh, single trial function here in this equations, partial differential equation. So we have this. Uh, the integral from 0 to 1 of the product of r and the given functions here. So uh, our function here is equal to our single trial function is equal to c t times pi x. So we have this r as a function of x and time. So, but we have to multiply this by sine of pi x here. So sine of pi x is our solutions. Okay, so we have the residual here. So by evaluating the residual, we have the c prime of t sine pi of x plus alpha pi squared c of t sine pi x. So Galerkin conditions, they must be equal to 0 here. The residual times the sine pi of x. So this is the sine pi of x is boundary conditions. If we substitute give the given in the these functions, we have the boundary conditions here. So by simplifying, we have this sine squared, then we have c prime of t plus alpha pi squared c of t. Then solve for this ODE. We have c of t equal to c sub 0 e of uh, e of the negative alpha pi squared t. Now find c sub 0 from the initial conditions using Galerkin again. So we have the from the initial condition here, this one. So we have the left side here, we have c sub 0 over 2. Equals to the expression, this is 4 over pi cube. So c sub 0 is equal to 8 over pi cube. So the final solution here is this one. So we can verify that using the integration here. So by using the Mathematica, so we have the Galerkin solution here, this one. We have the Galerkin solutions. We have the plot here of the Galerkin solutions. And we have the exact initial condition here. So we have also this. So they are almost the same. This one. We have the simulator here. So x from 0 to 1 here. So greater than 1, so we have no uh, we have no wave here. So we have only the plot for the from 0 to 1 here. So for a comparison, the exact solution is an infinite series. And this is the first and dominant term. Again, a single term, Galerkin gives excellent accuracy. So we have a summary now of all the problems. So problem number 1, 1D Poisson elliptic polynomials. Trial function, we use x times 1 minus x, or x squared times 1 minus x. So this is the exact solutions result. So they have the same, the exact solution is the same as the Galerkin solutions here. Then the problem number 2, we have a beam bending fourth order single sign functions. So we have the result here, the 0.4% error. Then for the problem number 3, we have 2D Laplace elliptic single sign hyperbolic sine functions, exact solution here. Then for the fourth problem, we have the 1D heat equation, parabolic single sign function with time coefficient, first mode approximations. So takeaway from these examples, the Galerkin method is not a singular algorithm. It is a flexible framework. You can use a polynomial for simple domain. Example 1, use a trigonometric function for periodic or beam problems. Example number 2, use a separated variable for 2D, 3D problems, 3D. Use a time-dependent coefficient for transient problems. Example number 4. So in all cases, the core idea is the same. Project the residual into the trial function space to get the system of algebraic or ordinary differential equations that are easy to solve numerically. So this is exactly what the commercial finite element software ANSYS Abacus COMSOL does at a massive scale. We have the references here.